Welcome back to ECE 442-542. We'll start with a few announcements. One is I'm extending the deadline for homework number 1 just because we haven't been physically connecting, and that homework will be due on the 30th of January. All the other deadlines should remain intact. The proctor agreement form, if you're an online student and you are using a proctor, get that in. If you're using Examity, make sure that you sign up with Examity to get a time allocated for you, a time window to take your exam. So if you're taking it through Examity, please get on UA Tools on the D2L website, click on Examity, find it or obtain a time that you can work with for your schedule in that 24-hour window for exam number 1. Homework 2 is due a couple of days before exam number 1. Exam number 1 is the 6th of February. There's some review material on D2L, and if we want a review session, we'll have to decide whether we want one or not, and that would be probably happening or be recorded immediately following the lecture on the 4th of February. Today what I want to do is continue with this discussion of having different ways of modeling a system. We've had difference equations, we've had state space, we've had block diagrams, we've had transfer functions. Let's now show another way of connecting those or relating those by finding a method for going from the time domain, difference equation, into the frequency domain and obtain a transfer function description. After we've now played with a lot of these frequency domain concepts, now we have a transfer function and it has a z floating around. Let's now become a little bit more comfortable with that, what that means in the frequency domain, and consistent or similar to how you found the Laplace transform of waveforms or signals, we'll define a z transform that's consistent with the Laplace transform. Now it's just for discrete time sequences. The sequence is now little x of n, and that's now a discrete sequence, and we want to now move that waveform or sequence into the frequency domain, and there is the definition of the z transform, and we'll try to give an intuitive feel for where that comes from, but it's really a way to go from time domain to frequency domain in discrete time systems. What we'll focus on more in this video really is using that definition and finding the z transform of some common waveforms. Let's start though, or finish up our relationship between different representations, time domain, frequency domain, and in particular for today we're going to look at going from a difference equation in the time domain into or finding a transfer function in the frequency domain. And before we looked at, or we found that this operator z to the minus 1 actually corresponds to a delay of a 1 sample period length of time. So the frequency domain operation of z to the minus 1, that's consistent with a 1 sample period delay, or holding on to something for 1 sample period. We're going to be finding the transfer function, which really means we want the underlying dynamic behavior of our system. We're not really worried about particular solutions or responses of the system. We really just want to capture the dynamical behavior of the system, and for that reason we don't need to keep track of the initial conditions when we z transform or take a difference equation into the frequency domain by using these operators of z to the minus 1. And this is what we're going to use. First, this first row says that the z transform, that's this script z with curly brackets, y of n, u of n. And now don't get too hung up on the product of these two waveforms. U of n really here is the discrete time unit step, and we're using that as a switch to turn on y of n. So y of n might actually be defined for all n from minus infinity to plus infinity, but with this particular product in place, now this really is converting this idea into really just sort of saying we are interested in y of n for n greater than or equal to 0. Because here u of n is equal to 1 for n greater than or equal to 0 and 0 elsewhere. That's what we're using for u of n. And it's really just turning off and on these different waveforms at the appropriate time index. Here, when the argument is 0 in u of n and non-negative, that's when u of n is active. Otherwise, it's equal to 0 and there's nothing to take the z transform of. So we will now say, oh, the z transform of y of n, u of n, we'll just let that equal capital Y of z. Then if somebody actually looks at a delayed version of that and they say, oh, y of n minus 1, I want its z transform, and we shift when it starts consistent with the argument, so we switch it on when u of n minus 1 is non-negative, and that will occur for all values of n greater than or equal to 0. I'm sorry, n minus 1 greater than or equal to 0, which now says that that time sequence inside the curly brackets is going to be true for n greater than or equal to 1. If we know that y of n, u of n, z transform is capital Y of z, then we can use this z to the minus 1 operator to say, oh, if we simply delay that by 1, this sequence, then we're going to say that its frequency domain representation is z to the minus 1, capital Y of z. That's what we're doing. And a lot of times here in red I've shown that it's implied that the sample period, capital T, is somewhere in that argument, but a lot of times it's just suppressed, and so we just say y at sample period n minus 1, and we don't say y of n minus 1 capital T. Hopefully that won't be confusing or won't cause too many issues when we simply start dropping or implicitly assuming that a given sample period, capital T, is present. So let's now start this process of going from a difference equation to a transfer function with an example. So we're converting a time domain, linear, difference equation, and it's really time invariant. We're not allowing these coefficients to be varying with time. Converting a linear, time invariant, time domain difference equation into the z domain to obtain a transfer function. And because we're interested in a transfer function, not the solution, not a particular solution or a given solution, we're not interested in keeping track of the initial conditions when we take the z transform, if we're wanting the transfer function. So let's now start with an example. Here we have some y's. We'll consider y to be our output and x to be our input. So now hold on or buckle up. Now we're using an input for x. Sometimes we use that as the state variable, but hopefully by context it's clear how these different variables are being used. Let's now take this time domain difference equation into the frequency domain, so that now we are shifting. Well, maybe I shouldn't use the word shift. We're now moving, transitioning from the time domain into the frequency domain, and now we want to z-transform each of these individual terms and come up with their frequency domain representation. If we z-transform capital or y of n, before we said, oh, we're just going to call that capital Y of z. A1, A2, B0, B1, those are all constant coefficients. Those will not influence the z domain or the z transform, so that now we have plus A1 z to the minus 1 capital Y of z. Since that second term is delayed by one sample period, then we have the next term, the third term, actually delayed by 2 sample periods, plus the last term on the left-hand side of the equality delayed by 3. And now that's equal to b sub 0 capital X of z plus b1 z to the minus 1 x of z. Let's now factor out these common transformed expressions y of z and x of z from the different sides, or we now can say that we have 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3 times y of z is now equal to b sub 0 plus b1 z to the minus 1 capital X of z. Where this expression will be considered our output z-transform, or the z-transform of the output signal, and x is now the z, capital X of z is the z-transform of our input signal, little x of n. With this expression, we can now solve for y of z over capital X of z, and dividing both sides by capital X of z and dividing both sides by this 1 plus a1 z to the minus 1, we end up with b sub 0 plus b1 z to the minus 1 over 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3. And as we've said before, we typically prefer these polynomials to be in powers, positive powers of z, so we can find that by multiplying by 1, where 1 is now z cubed over z cubed, and so doing we end up with this same ratio, y of z over x of z, being the same as b sub 0 z cubed plus b1 z squared all over 1 plus a1, whoops, we said we're multiplying it by z cubed, so we have z cubed plus a1 z squared plus a sub 2z plus a sub 3. There is now our transfer function that we found from a difference equation. And so now we have a way of going from difference equation to transfer function, and I hope you can play this tape backwards, meaning if somebody now gives you this transfer function, you can now multiply through or cross multiply and find this expression, and now you can distribute the y's and the x's through each of those terms, ending up here, and now you can go back into the time domain. So you should be able to find a time domain difference equation starting with a given transfer function description. That's what I mean by playing the tape backwards. And on exam 1, you're going to want to be able to rewind, play these different conversions forwards, backwards, maybe not sideways, but you get the point. You should be able to go back and forth between these different representations. Because what do we have? We have a block diagram. We could find the transfer function of that block diagram using block diagram algebra. Now we have this. We roll the tape backwards and we end up with a difference equation. We might have a difference equation. We can put that into a block diagram, or we could put it into a transfer function, or we could put it into a block diagram and then a state space representation. I hope you get the picture. We're scrolling back and forth, going many different ways, allowing ourselves the ability to see the same system represented in different forms. But now that we've seen these z's popping up a lot, let's go ahead and flesh out a little bit more information about the z, and in particular, let's define the z transform. And then we'll be having a lot of tools available to us, because now we'll have the z transform just like we have the Laplace transform for continuous time systems. And since that's the case, I'm hoping that you remember the Laplace transform. That's where we're starting from in terms of knowledge base. If we remember the Laplace transform, what did that look like? That was now the frequency domain version of a Laplace transformed waveform we would call capital X of S. Well, that was found by taking this integral, and let's just look at the one-sided integral for now. From 0 to infinity, that's when t is equal to 0 and going up to infinity. Here's our time domain waveform. So we have this waveform available to us from 0 all the way up to infinity. We weight it with this complex exponential e to the minus st, and we integrate from 0 to infinity using this weighting for each value of time t. And we could view this as a kernel, or this is just something, and this something is a special something. It's a complex exponential that weights all of x of t for all time. Obviously the weighting depends on the time t and the values of s, but that's now what I want us to remember relative to the Laplace transform, so that we can now move this into the z transform expression. Now to do that, suppose that we wanted to sample this time domain waveform little x of t. Well, to sample, we typically are saying, well, let's now just look at x at particular discrete time intervals, or discrete intervals of capital T. So now we're looking at t equal to little n capital T. If we plugged in, and that's how we would sample little x of t, but if we now use that same sampled structure for t in on this complex exponential, now we have e to the minus s in t, replacing little t with little n capital T, And we can now play around with the exponent because it's just now a product of three terms. What if we now rewrite that as e to the minus st raised to the n? Well, that's how you can think of it, and this expression, this complex exponential, is, and maybe what I should do is go ahead and, since that's not quite what I want here, because z we've already defined to be e to the st, so let me use that and pull out that minus sign so that now I have e to the st, which we've already agreed can be an advance, and that's what z represents. That's our operator in the discrete time setting for a frequency domain operator, raised to the minus n. Well, what if we do that? Now we have this sampled waveform, little x of t, sampled at every little n capital T points in time. That now gives us a sequence of numbers as n marches from 0 all the way up to infinity. And we're weighting that with z to the minus n. Again, n is the index that we're using. And we can now put that into a different transform operation, which is the z transform, where we now, if we're now playing with a sequence of weighted values, then we're not integrating, we're actually going to sum that sequence of weighted waveform values, so that now capital X of z becomes this infinite sum from n equals 0 to infinity of x of n, and again we're suppressing the actual sample period capital T, but this is now this waveform x sampled at every n sample periods, weighted by that same weighting z to the minus n, and in this case we will call this our one-sided z transform, since we're only looking at n on one side of the origin from n equals 0 all the way up to infinity. We'll call this the one-sided z transform. And obviously if we have a one-sided, we must be begging the point and saying, oh, we could also have a z transform that was designed or defined for all n, or when n transitions or moves from minus infinity all the way up to plus infinity, so that now capital X of z could be the same structure as the argument for this infinite sum, but now we have a two-sided z transform, and this is for n between minus infinity and plus infinity. That's now our definition. We have a sequence of numbers, x of n. We weight those by some complex power of n, of z, where z is actually minus, the power is minus n. But now we're just going to take little x of 0, scale it by z to the minus 0, little x of 1, scale it by z to the minus 1, x of 2, scale it by z to the minus 2, etc., and see what we can come up with for different waveforms, little x of n. So let's now look at some common waveforms, and that's how I will title this part of the lecture. Let's look at the z transform, or z transforms of common waveforms. And we'll just go through some of the standard waveforms. Let's look at a unit pulse. and I might, or that you might see this called different things at different times. I'm calling it the unit pulse, which means that it's 1 for n equal to 0. When the argument is equal to 0, it has a value of 1, and it equals 0 for any other values of the argument n. You might run across this and they call it the unit impulse, which that's really what's happening, except now this impulse has just a magnitude of 1. It's not like the impulse waveform in continuous time that goes all the way up to infinity in terms of magnitude. So this is like a Kronecker delta. We now have delta sub a of n, and maybe you will see that notation used. But that just means that it's 1, a value of 1. In continuous time, the area under that impulse is 1. Here we just have a magnitude of 1 to give us a value of 1 when the argument n is equal to 0. If we sketched that, here's our time axis, 1, 2, 3, and that just continues. We could say -1, -2, etc. But in this case, we simply are having a 1 here at time 0, and it's 0 everywhere else. So we have a 0 value for all other values of little n, and this is now our x sub a of n in the time domain. Now let's see what this waveform has as a z-transform. So let's now compute capital X sub a of z for this particular time sequence, and you can see that this time sequence is very complicated. That was a joke. But we can see, I hope, that this time sequence isn't very complicated. If we now look at this from, let's say that we wanted the two-sided z-transform, we would be looking at this infinite sum from -infinity to infinity of x sub a of n z to the minus n. That's our definition. Now we simply plug in the particular values for this time sequence x sub a of n. And we now have, and I think you can see that we don't even need to really worry about values of n less than 0, so let's just throw that away and say let's sum from n equals 0 up to infinity. And now we have x sub a of 0, z to the minus 0, plus x sub a of 1, z to the minus 1, plus x sub a of 2, z to the minus 2, and we just keep going. That's what that infinite sum tells us we're doing. But now we can plug in the particular values for this time sequence. X sub a at time 0 is in fact 1, but all of these other sequence values are 0. And now capital X sub a of z, this infinite sum is easy to compute. It's actually just 1, so now the z-transform of a unit pulse is just 1. Or the frequency domain, or the frequency response of x sub a of z, you plug in any value of z, and what do you get? You get 1. So for all values of z, or for all frequencies, z being this complex plane, all values of z have exactly the same frequency response. They have a value of 1. So that's sort of telling you why this unit pulse is powerful, or a unit impulse. It now effectively, if you viewed this as an input signal, you could say, well, what's its frequency content? Well, its frequency content now is telling you that no matter what the frequency is, you have the same frequency response. So now we're hitting, if we apply this waveform to any system, we're hitting that system with the same, or each frequency is being excited in exactly the same way. So that unit pulse is kind of a nice little waveform. It's maybe a little more understandable in the discrete time setting because it's just 1 at 0 and it's not infinitely tall with a area underneath it of 1 like we had in the continuous time case. Let's now look briefly at an aside before we look at common waveform B in this discussion. So before examining waveform B, let's just take a little bit of an aside. Suppose we now look at U of t as the unit step. Here's time, and the unit step, this is continuous time, we have a value of 1. Here is now our unit step, and this is the time domain. Now go back in your memory bank and tell me what is the Laplace transform of this waveform. What is capital U of s? And if you don't remember from your memory bank, you could actually go back to this definition of the Laplace transform, and hopefully using your calculus, you do remember your calculus. Hopefully you remember your calculus. You can now compute the Laplace transform of this unit step. This is now 1 over s. And what I want to do now is have us think about what does the pole 0 pattern look like for certain common waveforms. In this case, now this is the s-plane. Here's the real part of s, axis-wise. Here's the imaginary part of s. And now, what's the pole 0 pattern of capital U of s? Where are the poles? Where are the zeros? Hopefully you can see that here we simply have one pole at the origin. Poles are the values of s that cause the denominator to vanish. Zeros are the values of s that cause the numerator to vanish. We don't have any zeros, no open circles, and this now is our pole 0 diagram. Or this gives us now frequency domain information about the unit step in the continuous time case. That's the aside. Let's now look at that counterpart for a discrete time system. Let's now look at the unit step for a discrete time case. And now we have this time domain pattern for our waveform. It's 1, 1, 1, 1, and that's for 1, 2, 3, those values of n, and then it just keeps repeating. That's what those 3 ellipses, or that ellipses, mean here. And now this is b, x sub b of 1 with a magnitude of 1. So this pattern starts at 0, n equals 0, and goes on. It doesn't equal anything below n equals 0. Or we could write x sub b of n is now equal to 1 for n greater than or equal to 0, and 0 otherwise. You know what's coming. What's the z transform of this waveform? x sub b of z is now this infinite sum from minus infinity to infinity of x sub b of n z to the minus n. And that can be simplified. X sub b of n is 1 only for n's indices from 0 all the way up to infinity. So we can now rewrite this as n equals 0 to infinity of 1 z to the minus n. Or x sub b of z, now let's just write this down. We now have it's 1 when n is equal to 0 plus, again, this is an infinite sum. We look at what happens when n is equal to 1. That's now z to the minus 1 plus z to the minus 2 plus z to the minus 3. And that pattern just keeps going. And now we have this infinite series expression for x sub b of z. And that may look a little bit uneasy or uncomfortable. It's better we think of z transforms as some ratio of powers of z or polynomials in z, and this doesn't look like that at all. So now let's see if we can find a closed form expression for this infinite series representation of capital X sub b of z. But in particular, this is the z transform of a unit step, a discrete time unit step. But we now want to see, can we find a compact way of writing this, or a closed form expression where we might have a numerator polynomial and a denominator polynomial with bounded powers of z. Let's look at a closed form, or see if we can find a closed form expression for x sub b of z. And now I hope you're starting to remember what we've already looked at, maybe when we were talking about finding our mortgage payment, or actually how much we might have to pay back on our student loan. We had something similar to this. We had some infinite series that we had to find a closed form expression for. So now let's look at x sub b of z. That's 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. Now that looks a little odd, but we can clean it up a little bit if we realize that this is z to the minus 1 raised to the first power. This is z to the minus 1 squared. This is z to the minus 1 cubed. So now we just have these higher powers of z to the minus 1 being summed to form capital X sub b of z. Now, reminding ourselves of what we've done before, let's go ahead and, for starters, just write down x sub b of z, but we can get something similar to the first row that we wrote down by simply multiplying this by z to the minus 1, or a common ratio. If we multiply x sub b of z by this z to the minus 1, each term now is just going to have a z to the minus 1 additional factor. So we multiply 1 times z to the minus 1, and we obtain z to the minus 1. We multiply z to the minus 1 times z to the minus 1, and we have z to the minus 2. And now what's nice is we have the same tail of this expansion, or of this infinite series, in the first row as we do in the bottom row. And we can now use that to our advantage. The tail looks the same. If we compare the bottom to the top, and by comparing I'm meaning subtract the bottom from the top, now we simply have 1 minus z to the minus 1, capital x sub b of z on the left, we're just subtracting z to the minus 1 x sub b of z from x sub b of z. The tails look the same, so all of those terms cancel except for the very first one. And now we can see that if we divide through both sides by this expression 1 minus z to the minus 1, we'll end up with x sub b of z equaling 1 over 1 minus z to the minus 1. Now, we maybe pulled something a little bit fast and loose. When is this particular ... going to be well behaved? And by well behaved, I mean, when is this right-hand side actually going to sum to a bounded value? So we want to know, when is this... Otherwise, it doesn't make any sense. We're just... x sub b of z is some infinite value. We want to know, when is this infinite series expansion well behaved? And it's going to be well behaved. We're taking a z to the minus 1 and raising it to higher and higher powers. Well, the only way that something raised to a higher and higher power is going to have a chance of being bounded is if that something, that common ratio, that z to the minus 1, is, drum roll please, less than 1. If we start raising a number to a higher and higher power that's bigger than 1 or has a magnitude bigger than 1, that's going to go unbounded, so it will not be well behaved. But this right-hand side of both of these expansions will be well behaved as long as, or when, this common ratio, z to the minus 1, is less than 1. Where this is what I keep calling this common ratio, but that's the common factor between all of these terms. And that's the only time that this is even valid. The only time we can say that this is in fact going to be valid is when it's well behaved. If it's well behaved, that means this infinite series actually converges, so we could say that capital X sub b of z as an expression converges when z to the minus 1 is less than 1. So you'll see people talk about this in different ways, but now we know that this expression is true, is valid, as long as z to the minus 1 has a magnitude less than 1. And we can clean that up a little bit. That's the same as 1 over z being less than 1. The ratio of, or the magnitude of a ratio is equal to the ratio of the magnitudes. So this is now the ratio of 1 over the magnitude of z, and now we can multiply both sides by the magnitude of z, and we see that the magnitude of z, as long as it remains bigger than 1, then we will have this expression, capital X sub b of z, converging or true. So this is now what we have for a discrete time unit step Z transform. This is going to be true as long as Z is bigger than 1. And again, in this class we might prefer to write these ratios of powers of Z in terms of positive powers of z, so we can multiply both top and bottom by z, and we end up with an equivalent z transform expression. And what does the right-hand side of this z transform expression say? This is now our closed form expression instead of, and that maybe looks a little bit better than this infinite series that we had before. There's the closed form expression. This is the z transform of a unit step. And this little piece, the picture associated with that, is now saying, oh, all values of z, all complex values of z in the complex z-plane that have a magnitude bigger than 1 is where we have our region of convergence. That's all values of z that live in the region of convergence will allow this infinite series to be well behaved, and that's what we want to obtain, or to end up with this z transform of a unit step. And we can draw that picture of our region of convergence in the complex z-plane. We now have, here's 1, here's -1. We're outside of that, but we also have not only the real axis, but z can be complex. It can have imaginary components, so that now we could go up to j, that has a magnitude of 1, or we could go down to -j, that has a magnitude of -1. And now we have that's supposed to be a unit circle. What's our region of convergence? That's all of these values of z that live beyond this circle of radius 1. And we would then have this shaded region labeled as our region of convergence. All values of z that live out here allow this formula or expression for the z transform of a unit step to be valid. One more point that we could put into this picture of the z-plane would be our pole zero diagram for this transform expression. Where is our pole? What values of z cause the denominator to equal 0? Well, we set z minus 1 equal to 0, and we see that that's when z is equal to 1. So we have a pole at 1. Do we have any finite values of z that cause the numerator to equal 0 or to vanish? That would be a 0 or a finite 0, and in fact that's at z equal to 0 or the origin. So now for that unit step we can have this expression for its z transform. We could have this expression. Again, we have to consider or keep track of the region of convergence, which says that z lives outside of this magnitude 1 circle. And we also can see that we have poles and zeros, and that pole is right at 1. The region of convergence is outside of, or just larger than that pole. So the pole lives on this boundary of our region of convergence. That pole is not in the region of convergence. It's interior to this region of convergence. Let's now look at another common waveform. And the common waveform, before we maybe even get into that, let's just do sort of another aside. and examine the exponential waveform in the continuous time setting, or the analog signal. Suppose we now have the time axis t, and here is x of t, and what's the exponential waveform of x of t look like? And let's say that it's now x of t is e to the a t. And let's just make it causal, or for t greater than or equal to 0. And on the right hand side of that curly separator will be our Laplace transform expression, but you can see that what x of t looks like obviously depends on a. If a is bigger than 0, then this is going to just go unbounded. This is now a greater than 0, and so now our exponential grows. If a is less than 0, now we have this exponential decay that you were probably thinking of more so than that exponential growth scenario. But what is the Laplace transform of this exponential? That a now is a variable. We don't know whether it's negative or positive, so in that definition of a, the Laplace transform is 1 over s minus a. And if we looked at its pole zero diagram in the s-plane, here's the imaginary component of s, here's the real component of s. Now, if a was positive, we would be in the right half plane, and that would give rise to a growing time domain exponential waveform, or an unstable response. And this is now the pole zero diagram of an exponential. Let's see what that looks like when we are dealing with a discrete time version of that, or the digital exponential waveform. That we can now say is this x sub c of n, which is r to the n for n greater than or equal to 0. Again, we'll just look for n greater than or equal to 0, or this one-sided exponential to begin with. And where did that come from? Well, if we simply look at above the analog, and we sample that analog at integer multiples of the sample period, capital T, then we have e to the at, where little t is replaced with little n capital T. This is now e to the a n t, or this is now e to the at raised to the n. And this, if you just think of this as r, we now have r to the n, which is what we said we needed for the structure of a digital or discrete time exponential waveform. And what x sub c of n looks like in the time domain will obviously depend on what r has for a value. If r is less than 1, then as we hit r, let's say 1/2 squared, that's 1/4, 1/2 cubed, that's 1/8, 1/2 to the 4th. Now we have 1 over 16. That just keeps collapsing or exponentially decaying, so that now we have x sub c of n when r has a magnitude less than 1. That would look like an exponential decay, where this is now 1, 2, 3, 4 index-wise. That's for r less than 1. If r is actually bigger than 1, now we might start at the same value, but now we go unbounded exponentially as n increases. So this would be then a picture of x sub c of n when r is bigger than 1. And now what we want to do is say, what does the pole zero diagram look like for an exponential time domain waveform in the z-plane? Let's see if we can uncover that by a little analysis. So let's now say this is going to be the z-transform of x sub c of n, which is an exponential. X sub c of z is now, by definition, we just plug in our definition. This is n equals 0. We know we're starting or having non-zero values for little x sub c of n for n equal to 0 and bigger. Here is now x sub c of n, z to the minus n, where x sub c of n, again, is this exponential, which is thought of as r raised to the n for n greater than or equal to 0. Well, let's just write out some terms and see if we can see a pattern. We now have x sub c of 0, z to the minus 0, plus x sub c of 1, z to the minus 1, plus x sub c of 2, z to the minus 2, etc. X sub c of 0 is going to be what? We raise r to the 0, and what do we have? Well, whatever r is, raised to the 0 power gives us 1, plus x sub c at 1, well, that's just r to the 1, z to the minus 1, plus r squared, z to the minus 2, plus r cubed, z to the minus 3, etc. And what's that going to do? Well, maybe it's not clear what's happening there, but let's now see if we can rewrite it into a form that looks a little bit better, where maybe it's something that just gets raised to a higher and higher power. And we can see that if we say, oh, that's r z to the minus 1 to the 1, plus r z to the minus 1 squared. All of this r's and z to the minus 1 are raised to the same power, so that's now our common ratio, is this r z to the minus 1 cubed, and that pattern just keeps going. So there's our geometric series. And when is this right-hand side going to be bounded, or when will it converge? When will we have a finite value associated with capital X sub c of z, this infinite series expansion for capital X sub c of z? Can we find a condition when this sum actually is bounded, or when does it converge? What do we know about our common ratio? This converges as long as, what do we know has to be true about that, the magnitude of what we keep raising to a higher and higher power? This is now our common ratio. Well, we know that that needs to be less than 1. And if that's true, now we can start playing or using our strategy to find a closed form expression for capital X sub c of z. This is now 1 plus rz to the minus 1 plus rz to the minus 1 squared. Well, that's a big 1. Plus rz to the minus 1 cubed, etc. Well, now we can just get something with the same tail. We want to be able to basically cancel tails in these infinite sums, and we can do that by multiplying that same formula by the common ratio. One times that common ratio just gives us the common ratio, which is over here. And then we just raise it to higher and higher powers. And that gives us the same tail. We can compare the top line with the bottom line. And because the tails are the same, those cancel. And we're left with 1 minus rz to the minus 1 times capital X sub c of z equaling 1. And we can solve that for capital X sub c of z. That's now 1 over 1 minus r z to the minus 1. And we know the condition under when that converges. This is now 1 over 1 minus rz to the minus 1, or we can clean that up and say, let's multiply both top and bottom by z, or we're multiplying the whole thing by 1. That now gives us z over z minus capital R, and that converges or is true for what condition? Well, that is true as long as our common ratio had a magnitude less than 1. Well, we can write that as r over z less than 1. Again, we can take this magnitude of a ratio as the ratio of the magnitudes, and we see that now the magnitude of r, or probably the better way of saying that, is the magnitude of z. All complex values of z that have a magnitude bigger than r are in the region of convergence. And this is now what we can draw. We can say that we have a pole at R, we have a 0 at the origin, and our region of convergence is all values of z that are beyond R. So if I could pull out my compass and draw a circle of radius capital R, then the region of convergence lies beyond that magnitude of R, or that radius, in the complex z plane. This is just our z plane. We now know what the pole zero diagram looks like for a exponential time domain waveform. It now has a pole at R, has a 0 at the origin, and our region of convergence, or the values of z that allow this transform expression to exist, will be for values of z that are bigger than R. We can make a couple of observations. Note, the region of convergence, this ROC, that's how I might refer to it, the rock, the region of convergence, the rock, is outside R, And we didn't make any claims on R, did we? Right now. We didn't say it was less than 1 magnitude, or oh, it had a magnitude bigger than 1. We didn't make that condition on this derivation. So the region of convergence is outside R no matter what, whether R has a magnitude less than 1 or R has a magnitude bigger than 1. The region of convergence is outside. It goes off to infinity. The region of convergence is going, it's expanding from R all the way out to infinity. So it includes infinity. The region of convergence is outside of R. Whether R was bigger than 1, let's say R was 2, the region of convergence has what? This hole in it of radius 2, and it goes outside of 2, or R could have been 1/3. Then we would have the region of convergence living beyond 1/3, but it's still beyond that radius of 1/3. The time domain response is unbounded under what condition? Here is our time domain expression. Little x sub c of n is equal to capital R to the n for n greater than or equal to 0. When is this time domain expression, what did I say? Unbounded. When is it unbounded? For what values of R? If R has a magnitude bigger than 1, the time domain response is unbounded. The time domain response is bounded if R has a magnitude less than 1. But where's the region of convergence? For either of those, it lies beyond R. Hopefully that's clear. So that's for this time domain waveform. This structure in the time domain could be either unbounded or bounded. The region of convergence structurally looks the same, but it will have a smaller or larger hole in its interior depending on what R is. So the region of convergence structurally looks the same, but where exactly it begins, which is beyond R, will depend on whether R is bigger than 1 or less than 1. And if R is bigger than 1 in magnitude, the time domain response goes unbounded. If the time domain response is bounded, we know that we must have had an R, which we're raising to higher and higher powers in n, must have been less than 1. Try to wrap your head around that, but now this picture looks the same no matter what R is. If R is less than 1, then that pole, we could locate the unit circle now. 1 might be here if R was less than 1. If R was bigger than 1, then the unit circle would have been there, one of the boundary points of the unit circle. And that pole would have lived outside the unit circle. So don't confuse this dashed circle with the unit circle. This is just the boundary of our region of convergence. And we'll pick up with that the next time we're together.